Good morning, guys. I hope you're doing well. Welcome to another Monday morning. Again, we have two more topics that are covered on the next test. We're going to do one more lecture after that before we're done with material for the next test. So you need to make sure that you get your first test back. Those will be done by Wednesday. I will make sure that there's a lot of feedback on those tests, and I am willing to go over anything and everything that you guys need. Once you get your feedback released to you, you should be able to see the questions and the correct answers, so that will be available for you to study with going forward. Do we have any questions, comments, problems before we get started on everything?
Is anything
Okay,
from
so let's go ahead and get started. We're going to be talking about bonding and dot diagrams today. And you'll see that there's a very long list of topics. It seems like a lot. It's actually not as bad as it looks, because they're almost all very small things that tie into everything that we're doing. And there's very little math that goes into what we're talking about for this and the next topic. So hopefully that will be a nice welcome break for some of you. I was not happy without the math, but that's okay. But let's do a little bit of review from what we've talked about in the last lecture. So first thing we want to talk about, 64.85 grams of Na3PO4 were dissolved in 725.3 milliliters of water. What's the molar concentration of that solution? So I got a question, is there anything from exam 1 that's explicitly going to be on exam 2? Well, not exactly. It's not like there'll be a specific question that comes directly from exam 1. That's not really how that works. But since everything builds on what we did in exam 1, there may be something that looks like an exam 1 question that's tied into material for exam 2. There's nothing that's specifically pulled from exam 1 materials. So hopefully that helps. Okay, so if I want to talk about molar concentration, we have 64.85 grams of that Na3PO4. 64.85 grams of Na3PO4. And if I want a molar concentration, I have to have a molecular weight. So if I see my Na is 22.990, multiply that by 3, I add to that the mass for the phosphorus, which I have here as 30.974. And again, periodic tables are a little bit different. The one that I'm using is the one that's on my desk, which is a little bit bigger than the one that's on the exam handouts. It's easier for me to see while I'm doing this. Plus 4 times that 15.999. And I get 163.94 grams of Na3PO4 per mole. If I want a molar concentration, that needs to be in moles per liter. So while I'm currently in moles, I need to have liters. So I'm going to divide by the 725.3 milliliters and then convert that from milliliters to liters. So that'll cancel that and leave me with moles per liter. So 64.85 divided by the 163.94 divided by the 725.3 and multiplied by 1,000. And that gives me 0.5454. Yay. Oh, that doesn't fit. 54. So 0.5454. And that's molar. Again, moles per liter. If I dilute the above solution by taking 15.32 milliliters of solution and diluting that to a final volume of 25, what's the final molarity? Okay, so we're talking dilution. That's an M1 V1 equals M2 V2. My M1 is that number that I calculated right there. My V1 is the 15.32, and my V2 is 25 milliliters. So my final volume. I'm looking for M2. So if I have M2 is equal to M1 V1 over V2, I have 0.5454 molar, and I multiply that by, trying to find a way that's going to fit in the space that I have, sorry, 0.5454 molar, 15.32 over 25. And again, since both of those are milliliters, that will cancel, leaving me with an answer in molarity, which is what I'm looking for. And that gives me 0.3342 molar as my final molarity for that. Okay. All right. Questions so far? Okay. A 64.38 milliliter sample of an unknown acid, HX, has reacted with NaOH. One HX reacts with one NaOH to give NaX in water. Okay, so I'm going to take a look at that and go, all right, I don't know really what that means, but it says HX reacts with NaOH, and that gives me an NaX plus H2O. So I can tell from looking at this that it's an acid-base reaction, and I know that also because it says it's an acid, and I know that NaOH is a base. That's an acid-base reaction. Okay, fine. And it's a one-to-one relationship. 27.32 milliliters of 0.02 molar NaOH. So this is 0.0200 molar. And I used 27.32 milliliters of that to do this titration. That's required to neutralize the HX acid, which has a volume of 64.38 milliliters. Now, as we've done previously, we start with the thing that we know the most about. So I know the most about that NaOH. I have 27.32 milliliters of NaOH. I will convert that to liters, and then I'll multiply that by the molarity, 0.0200 moles of NaOH per liter. That will leave me an answer in moles of NaOH. I know that 1 mole of NaOH is required to react with 1 mole of HX. And I want to know what the concentration of that HX is. So if I have moles, then I need a volume for that HX. And that was 64.38 milliliters. So I'll divide by that volume and then do the conversion from milliliters to liters. That'll leave me with moles per liter of HX. And I get as an answer 0.011 4 sig figs 1159 molar. Okay, so that's the molarity that I get. Now, if the mass of the acid added to make the solution was 686.71 milligrams in 1 liter, what's the molar mass of the acid? And therefore, what is the identity of the acid? Okay. So I'm looking at this going, right, so I have 686.71 milligrams in 1 liter. Okay. I also know that the molarity, the moles per liter, is given right here, right? So that's moles per liter. So I can look at this and say, all right, I can get rid of the liters. If I divide by the 0.01159 moles per liter. Now, why did I do that? Because I wanted to get rid of the liters. That's all I'm doing. And that gives me a milligrams per mole. And in my head, something clicks when I do that. And I say, oh, I want a molar mass. That's grams per mole. So if I flip that, then I should get something that looks like, if I convert the milligrams to grams, then I should get grams per mole, which is what I'm looking for, right? So I can do a conversion from milligrams to grams. I know that 1 gram is 1,000 milligrams. So 686.7, I divide that by the 0.01159, and I divide that by 1,000. And that gives me 59.2, decimal place is in the wrong place. 59.249 grams per mole. Okay, awesome. I got a grams per mole. That's a molar mass. That's awesome. Now, 59. And I look at that and I go, right, 59. Well, I know that H is 1.008, right? So I can subtract the mass of the H from that. And if I do that, that leaves me with a mass of 58.2414. And if I look at my periodic table, I can see, and my math is again wrong, I can't believe I did this again, I would find something that is approximately that mass on the periodic table. So if I see 58.24, right, is close to 58.933. So I would say that that's probably a cobalt, HCO, just based on the mass that I'm looking at. Okay, that's all I did. Now, I could say it's cobalt. I could say that it's nickel. Either one of those is perfectly fine. Your logic in determining which one it is perfectly okay. It's all based on that math. Now, questions about what I did or why I did it?
Yeah, how did you get 58.2414? What did you subtract 59.249 by again?
I will tell you that number 4 will not be something I will ask you on a test, but there's that. All right, if there are no questions, then let's talk about the non-math stuff. So we need to talk about valence electrons. Okay, now valence electrons is something that we've talked about without specifically talking about it in the past. And let me pull up my periodic table and show you what I mean by that. So when I talk about any row, let's talk about this row 3, right? I'm talking about these guys that are here: sodium, magnesium, aluminum, silicon, phosphor, sulfur, chlorine, and Ar. So row 3. If I talk about these, I know that if I'm one of these metals over here, I'm trying to lose electrons to come back and be like neon, right? And if I'm over here and I'm a non-metal, I'm trying to gain electrons to be like argon. Now, it doesn't matter which direction I go. They all want to be that noble gas. Everybody wants to be a noble gas. The question becomes, why? Well, it turns out that there's a lot of stability that comes from being a noble gas. And that's because this S block over here, these are full, and my P block over here, these are full. That means that in that outer energy level, my S and my P, those are completely full. If that's true, I have 1, 2, 3, 4, 5, 6, 7, 8 electrons that are present in that outer row. Okay, and then any row is going to be like that, because if we talk about row 4, this right in here, this D group is going to be a 3D, not a 4D. So the only 4 electrons that are here are going to be these S and these P. Okay, so in our outermost energy level, we're always talking about having a stable octet. Okay, that's where the term stable octet comes from. Okay, we're trying to make sure that we have 8 electrons that exist in that outermost level. Okay, and if I'm one of these metals, I can do that by losing these 2 from this group to make sure that my group group prior to that, group 3, is completely full. There's nothing in the 4. Okay, so that's what we're trying to do there, is to make sure that we've got those 8 electrons, those 8 valence electrons that are there. But I know, unfortunately, that I can't always do that. So let's go back and look at our slides. Now, if we talk about carbon, and I want to talk about how many electrons he has in total, let's talk about our carbon. So carbon is number 6. He has 6 total electrons. Okay, that's awesome. So 6 total electrons, 2 of which are in the 1s. So he's a 1s2. And then he's a 2s2 and a 2p2, right? So he's got 2 in this 1s, 2 in the 2s, and then 2 in the 2p. So that's his electron configuration. And I know that because they're in different suborbitals, the s and the p, then I know they're not in the same physical space. I also know that those ones are inside of the twos, right? The 2 is further out. So there are 2 energy levels, 2 different distances from the nucleus, and there are 2 electrons in each s orbital and some in those p's. Okay, awesome. So carbon has 2 electrons in the 1s, 2 electrons in the 2s, and 2 left over. So in that outer shell, that level 2, right, then I have 4 electrons that we're talking about. 4 electrons that are in that outer shell. Now, they're not all available exactly in the same way, because some of them are in S and some of them are in P, so they're not exactly the same. Their energy levels are slightly different, but they're not the same, okay? That's not that important, but that is absolutely true. I'm not going to say it's not. Now, the electrons in the highest energy level, the highest quantum number, and the highest angular momentum are called valence electrons. Those are the electrons that we can work with in bonding for molecules or in making positive ions called cations, okay? So if we're going to transfer electrons to that, we would do it in that outermost energy level, okay? So we'd be adding to the 2p here. We could take away from 2p or 2s, okay? So that's where we're going to be dealing with that. And those electrons that are in that outermost group, this level 2 for carbon, those electrons are his valence electrons. So nothing that's in the completely full 1, but everything that's in the 2. Questions about that? All right. Now, one of the ways that we bond is through ionic compounds, okay? So they're going to lose electrons, gain electrons to be like the nearest noble gas. Yay, we talked about that, okay? And that's because they want to be a noble gas. Everybody wants to be a noble gas because there's particular stability in doing so. Okay? 8 total electrons that come in any of these noble gases. 2 from the S, 6 from the P. Okay? And there, again, is that stable octet. All right. So it's easy to lose electrons from over here in that S group to become like the nearest noble gas, the one prior to it. Okay. But it's harder to do that when I get over here. I have to either lose, like for silicon, I have to lose 4 electrons to be like neon. I'd also have to gain 4 electrons to be like argon. Not exactly the greatest thing. And so we find that some of these non-metals tend to not make ionic compounds. They don't. And we've talked about the nomenclature that goes with that. The non-metal to non-metal, those are named differently because it's a different type of bonding. Okay? Talked about this. So the octet rule, having those 8 that we're looking for. So full S, full P, 8 electrons that we're looking for. So again, ionic bonds, we lose or gain electrons to be like the nearest noble gas. And then that electrostatic charge that's generated because I've made an ion, those are attracted to each other. That's an ionic bond. Okay? And if we talk in detail about sodium chloride, I know that sodium is a metal. All right, he's right here. He's in 1A. So if we talk about just sodium, he's got 1s2, 2s2, 2p6, 3s1. And that's where I get this electron configuration here. It loses that 3s1 electron to become 1s2, 2s2, 2p6, which is the exact same configuration as neon. Okay? And it has in that outermost level, that level 2, 8 electrons. So the 6 plus the 2 gives me the 8. All right. we talk about the chlorine. So he's over here. So he also has a 1s2, 2s2, 2p6, 3s2, and he's currently 3p5, right? So that's his native configuration that's given here with that 3s2, 3p5. I know that he wants to become like argon, so he's going to gain 1 electron to do so. And when he does, his electron configuration is just like argon. It's 1s2, 2s2, 2p6, 3s2, 3p6, which is the electron configuration of the argon. Okay. And again, that charge that's then generated on each of those is attracted to each other. Okay? So that's how ionic bonding works. We transfer those electrons. So now I have an Na plus, a Cl minus. Those two ions are attracted to each other to form the NaCl bond. That's an ionic bond. Anytime you have two ions next to each other, any ions, it's an ionic bond. Ionic bonds tend to be metal to nonmetal bonds. Now, what you're looking at here, this picture, okay, is what we call a Lewis dot structure. So the way that we do this, and we'll talk in much more detail about this again in just a minute, but we show the electrons that are in the outermost group, right? So that sodium has that 3s1. That's why how he ends up with being like this, okay? And you know that chlorine has a 3p5, right? So he ends up being like this. And the only reason that I've symbolized those electrons differently is so I can tell where they came from. That's all. It's just visual for me. That's it. So now I know that those two things can come together, and when they do so, then we have a happy situation, right? Because what actually happens is that the Na loses this electron and it comes over here to this chlorine, and so then I have an Na that has no electrons around it, or a complete full octet from the inside, and then the chlorine that has that full octet that it now has all to itself. Yay, awesome. Okay. Now, like I said, we're going to talk in way more detail about how we draw those Lewis structures. But they're, again, just a representation of the electrons in those outermost energy levels, those valence electrons that we're talking. Okay? So that's how that works. We transfer that electron from Na to Cl, and that's an ionic bond. It's a complete transfer of electrons. Okay. But I can't always do that. So when I can't do that, then we have to talk about a different type of bonding. So let's talk about one of our great examples of nonmetal to nonmetal bonding, which is water. I have 2H and 1O. I know that neither one of those becomes charged, so it's not a complete transfer of electrons. Okay, so it takes a lot of energy to transfer electrons. The ionic bond that will be formed does not have a favorable stable structure compared to the non-ionized H and O. But that oxygen still wants to behave like this Ne, right? So it still has an attraction for two electrons. It really wishes it had them. And that hydrogen, the easiest way for it to become a noble gas is either to gain an electron to be like He, or to lose one so that it doesn't have that electron sitting in that outside shell, right? But it doesn't actually want to lose that electron. I mean, it really is not favorable to pull that electron off of there. So it wants to lose it, but it's not capable of losing it in this case. So there's something else that we can do. We can share electrons. And that means that oxygen is looking to make two bonds, so that it has two more electrons that are available to it, so that then it will have the 8 around it. And hydrogen is looking to make one bond, because then it will have two electrons around it. That sharing of electrons is called covalent bonding. Now, sharing of two electrons, one from each atom, makes a normal covalent bond. So we have normal covalent bonds. We also have ones that are not normal. Okay. So if they all come from one side, then that's considered a polar donation. We'll talk about that a little bit later. Now, I think of the state of electrons kind of like a divorce where there are kids, right? those kids are either shared 50% to each parent, covalent bonding, complete sharing between the two, or they spend not equal time with both parents. So that's considered polar-covalent bonding. I spend more time with one of those parties than the other one. Or only with one parent, and that's ionic bonding. Okay? So we have all of those that exist. And what determines that has a lot to do with what the electron configuration is to start with. Now, the other thing that we have to talk about, when oxygen bonds with two waters, only 2 of the 6 electrons in oxygen are shared. Okay? Sharing 2 electrons from 2H means that there are 8 around the oxygen. The electrons that are not being shared with H are called lone pairs, and we'll show you exactly what that looks like in a few minutes. Now, the determination of which situation is going to be, whether it's going to be complete sharing, partial sharing, not sharing, has a lot to do with 1, how many electrons are in that valence shell, 2, how electronegative that species is, i.e., how much does that particular species pull the electrons that are in a bond, their Lewis dot structures, and the octet rule. So those are the things that we're going to be talking about. So do I have any questions so far? Okay. Now, Lewis dot symbols. Lewis dot structures explicitly show the electrons in the valence shell of the atom. So for oxygen, there are 6 valence electrons. So the 2, 1, 2, 3, 4, 5, 6. And so we get 1, 2, 3, 4, 5, 6 here. For hydrogen, we have 1 in that 1s. So H looks like this. Okay. And when they're bound, I end up with the oxygen making a bond with hydrogen, the oxygen making a bond with the other hydrogen, and then we get the sharing of those electrons. So hydrogen donates 1 electron, oxygen donates 1 electron. Oxygen donates 1 electron, hydrogen donates 1 electron. And now, if I look around, oxygen has access to 8 electrons, and that hydrogen has access to 2. Because he's in that first row, he can only have access to 2. Okay? Hydrogen and helium are both, instead of being stable octets, they're stable duets, but they're the only exceptions to that. Okay? So that's the kind of sharing that we see for those oxygen and the hydrogen. When I draw a Lewis dot structure for a particular atom, I do it based on its valence electrons, just like I did here. So oxygen has 6, 1, 2, 3, 4, 5, 6. Okay. And hydrogen has the 1. So that's where that comes from. And then we try and make a bond in such a way that we have a stable octet and or stable duet for all of those species. Now, since oxygen is sharing 2 electrons with H, and the 2 electrons from the 2 H's, and the 2 lone pairs, there are 8 electrons around that oxygen. So again, 1, 2, 3, 4, 5, 6, 7, 8 that are around that oxygen. Okay. The sharing gives oxygen access to 8 electrons and H access to 2. All right. Hydrogen only has space for those 2, so that's why that's like that. Okay. Cool. Questions about that part of it? So let's draw the atomic Lewis dot structures for C and O. So carbon, being here, has 4 electrons in its valence shell, 2 from the S and 2 from the P. Okay, so 1, 2, 3, 4. I've randomly distributed those around this. We'll talk about how you know where to put those things. At this point, there's no reason to put them in any given place. But I know that in my head, I know that since they need to make an octet and there can be 2 electrons in a particular sharing of things, like in one orbital, then I can have, for those 8, I can have groupings of 4. So 4 groupings. That's why I have the 4 distributed the way that they are. Oxygen, again, has 6, 2 from the S and 4 from the P. So that's where I get these 6. 1, 2, 3, 4, 5, 6. And again, I put 2 of them as lone pairs and then 2 available for bonding. Now, I know that I can make CO2, and we see that written all the time. How do I combine carbon, oxygen, and oxygen to fulfill the octet rule? So I can combine one oxygen electron with one carbon electron to make a bond, and the same on the other side. So if I do this, I can see that I have 1, 2, 3, 4 that are around this carbon, and 1, 2, 3, 4, 5, 6, 7 that are available to that oxygen. I have not made the octet yet for anybody. That's not a great situation. So it's not fully happy, and I know it's not fully happy. So I know it's not happy, and I haven't figured out how to get it happy. So the first thing that we need to do is talk about what are the rules for doing this? Because I know that I've done something that's not quite what I'm looking for before, but I don't really know why. Okay? So let's talk about that. The set of rules will not be on the test. You'll have to know the set of rules. And the rules will be shown on the next slide. And just as with solubility, the rules were applied in order of appearance. We're going to be talking about the following molecules: PCl3, NH3, and BrO3 minus. Those are the three that we're going to be talking about. So let's talk about PCl3 first. Now, we're going to take and sum the valence electrons from all atoms, and we'll take any charge that exists into account. So when we talk about that BrO3 minus, we'll need to include that minus charge. So that means an additional electron. We'll write the symbol for each atom, and then connect atoms with the bond signaled by a line. Each line is 2 electrons. We'll complete the octets around all of the atoms bonded to the central, so anything that's bound to that central atom. We'll put any leftover electrons on the central atom, and if there are not enough electrons to give the central atom an octet, we're going to try multiple bonds. Okay? I'm sure that all looks like a bunch of Greek. I'm very aware of that. So let's talk about what that's going to look like. We'll come back and reference this list again. If I want to talk about PCl3, I know that I have a P and I have 3 Cl. Phosphorus is here, so I know that I have 1, 2, 3, 4, 5 electrons from phosphorus. That's where this 5 comes from. I know that chlorine is right here, and that means he has 7. So 1, 2, 3, 4, 5, 6, 7 valence electrons, and there are 3 of them. That gives me a total of 21 electrons from chlorine. If I add all of those electrons together, that gives me 26 electrons that I need to deal with in this structure. That's how many electrons are present. I need to put them somewhere. Now, I put the phosphorus in the middle. He is the thing that I put first, that's written first. So he goes in the middle. That's the way you're going to do this. Whatever's written first, that goes in the middle. Now, is that always the case forever and ever and ad nauseum? No, but that's the way I'm going to handle it. For this class, if it's written first, that's what goes in the middle. So phosphorus goes in the middle. I write a chlorine, and a chlorine. So if I were drawing this, I would be looking at this. Okay, awesome. Now, I can either draw a line or I can put 2 electrons in between. Which you do is entirely up to you. It doesn't matter to me because I know that this line represents 2 electrons. So I can take it that way, or I can explicitly show that there are 2 electrons there. I don't care which one you decide to do. I tend to use the like this to indicate that they're a bond. That tends to be the way that I do it. So that's what that means. Okay, fine. So I have a total of 26 electrons. Phosphorus had 5 electrons. There's 1 of them that gives me 5 from the phosphorus. The chlorine each has 7. There are 3 of them. It gives me a total of 21. Then I have 26 that I need to deal with. This is the same math that you're looking at up here. I'm just showing you what I would do with this. When I draw those bonds, that takes 2, 4, 6 electrons that are now taken out of that. And that leaves me with 20 left that I need to deal with. The next thing that it says to do in my list, complete the octets around all the atoms bonded to the central atom. Okay. So that means the chlorines. So 1, 2, 3, 4, 5, 6. And I give it 6 because it already has access to 2 right here. So if I add 6 to it, that means it has an octet. I do that for each of those chlorines. So 6 times 3, 18. And that leaves me with 2 additional electrons that need to be dealt with, right? So it leaves 2, and according to these rules that I had, any leftover electrons go on the central atom. It's number 4. So the central atom then gets these 2 electrons right here. And if I look at that structure, I can see that each chlorine has access to 8 electrons, 2, 4, 6, 8. All of them the same, so all of them have 8. And then the phosphorus has 2, 4, 6, 8 as well. All of the octets have been satisfied. This looks like a good structure, and it actually is. This is the structure that would exist for this particular molecule. Questions about what I did or why I did it? Okay, let's take a look at another one, because it helps if we look at many. So again, this is my overall structure that I'm going to get, this thing that I've already drawn up here. So this is what we'll end up with. I'm going to show you in detail how I got that. So nitrogen, 1, 2, 3, 4, 5 electrons. So my N has 5. There's one of those, so that's 5 from the nitrogen. I have 3 hydrogens. Each hydrogen has 1 electron. So that gives me a total of 3. That means that I have 8 that I need to deal with. If I put the nitrogen in the middle, he's written first, so he goes in the middle. Hydrogen, hydrogen, hydrogen. At this point, it doesn't matter where I put them, really doesn't. I draw 1 bond in between all of them. That's 2, 4, 6 electrons that I've taken out of that. I lose with 2. Those 2 electrons go. Now, the next thing I'm supposed to do is fill the octets for the outside. But remember, hydrogen doesn't need an octet. It needs a stable duet. So that each of these hydrogens is happy because there are 2 electrons here. So those 2 electrons that are left come to the nitrogen, and they go right there. Now that's how I get that structure that I'm looking at there. Questions about that? Okay, let's try one more. And I'm going to end up with a structure that looks something like this. And you'll see that there are brackets around this and a negative charge on the outside. And that's because this thing actually has a negative charge. So we need to indicate that in some way. There has to be a way to account for the fact that there's an additional electron. But let's start at the beginning. I have a bromine and I have some oxygens. I know there's 1 bromine. I know there are 3 oxygens. And then I have a lone, a negative charge. So I know I'm going to have to include that right there. So that's 1 that comes from that charge that exists. So there's an additional electron because of that charge. If I look at my bromines, they're right here. Okay, since they're halogens, that means they have 7 valence electrons. 2 from the S, 5 from the P. So the bromine has 7. 7 from there. Oxygen, being a chalcogen, has 6. Okay, 2 from the S, 4 from the P. So that's total of 18 from those. 18 plus the 7 plus the 1 gives me 26. So that's 26 electrons that I'll need to distribute. As always, we're going to write our BR, an oxygen and an oxygen and an oxygen. And then I'll need those brackets and the negative charge because it is charged. So I need to make sure that I've indicated that. I always do that next because I don't like to forget about it. I draw 1 bond in between the bromine and each oxygen. And that gives me 2, 4, 6 that I've taken out of that. That leaves me with 20 electrons that are left. Okay, fine. So then I'm going to go and fill my outside octets. So 2, 4, 6 on each. And of course, if I take that and subtract the 18, that leaves me with 2 left, which then end up on the bromine. Okay. Now, if I look at this, I see that each oxygen has access to 8 electrons. There's 2 there, and then the 6 that it has, 2 here, and the 6 from the lone pairs, 2 here, and the 6 from the lone pairs, and then that bromine right there has 2, 4, 6, plus the 2 in the lone pair, which gives me 8. Now, given what I know at this point, this looks fine to me, right? I have no reason to think that this isn't fine. But I'll tell you right now, it's not fine. And that's because we haven't taken everything into account yet. We had to get this far to be able to talk about this part of it. But let's talk about the next part. Are there any questions about how I got where I am? So the next thing we have to talk about is formal charge, right? Now, formal charge is an electrical charge difference between the valence electrons in an isolated atom and the number of electrons assigned to that atom in a Lewis structure. That's the formal definition. And there is some math that can go with this, but this is not the normal way that I handle it. You'll see this on the slides. It can be done this way, but it's not always the way that we talk about it. Okay? So a formal charge is equal to the number of valence electrons minus half of the bonding electrons minus the non-bonding electrons. And we only do this looking at the formal charge after we've made the structures the best that we can. So all unshared non-bonding electrons are assigned to the atom that they're on. For any bond, half of the electrons are put on each atom in the bond, and this is done for all atoms in the structure. Now, a formal charge is not real. Please understand that this is just bookkeeping. It's a way for us to be able to evaluate this structure to see if the electrons are likely to be in that configuration. Okay? So that charge doesn't really mean anything, but it's a way for us to look at, how happy is this structure? Is this a good structure or a bad structure? That's all it is. It's bookkeeping. All right. So let's talk about Cn minus, right? If we talk about Cn minus, I know that carbon has 4 valence electrons. That's how I get this 4e right here. Nitrogen, being the next one over, has 5. And there's a negative charge, so that's an additional one. So that gives me 10 electrons they need to distribute around this thing, right? So I have a carbon, I have a nitrogen. Neither one of them is really central because I only have 2 of them. I need 10 electrons. So I need to draw at least one bond. When I do that, it takes 2 of those out. That leaves me with 8, right? And those 8 electrons, it's like, well, okay, where do I put those? Well, all right. If I say that carbon is the center, because he was written first, so I would assume he's the center, then I would distribute those 2, 4, 6 there, and then 1, 2 there. Okay. 6 for the nitrogen, I'll do 2, that's where I get that. And of course, this is a negative charge, so that's how I get this. And I look at that and go, right. I'm not sure that I'm happy. And I know that I'm not happy because if I look at that, carbon doesn't have enough electrons around it, right? It has access to the 2 from this bond, and it has access to the 2 in this lone pair, but that's only 4, right? And while nitrogen has access to 8, it just doesn't feel right. Why are all the electrons on the nitrogen? And it could be, but I don't think that's really how it's going to do it, because the point of this was to share electrons, right? So if we're going to share electrons, shouldn't we share in a way that makes everybody happy? That's usually how this works. So what we do in this case, we can look at something called the formal charge. And so my formal charge for carbon in this particular drawing would be equal to the number of valence electrons that carbon brought to this party, which was 4. So that's the number that I had up here. So that's how many he brought to this party. And then going to subtract half of the electrons that are in the bond. So I assign that bond 1 electron to the carbon, 1 to the nitrogen. So half of that 2 would give me 1 that's assigned to the carbon, and then minus its lone pairs, it's got 2 electrons in that lone pair. So that's going to give me 4 minus 1 minus 2 gives me plus 1. So it has a charge. Okay. Now, if I look at my formal charge on nitrogen, nitrogen has 5 electrons that are supposed to be given to it. There are 2, 4, 6 that are in those non-bonding pairs, and 1 from the bonding that's there. So that's actually 7 that are assigned to it, right? And so that means that the nitrogen has a -2. And that's a lot of formal charge, right? And I knew that didn't feel right in my gut. And I looked at that and said, okay, it doesn't feel right. So now we talk about this formal charge, and it has a bunch of formal charge. So how do we take care of that? That's what this formal charge is for. We can see that because it has formal charge, it's not a happy structure. So I can try and rearrange things. And the way that I rearrange things, I'm going to take this line out so that we can look at just the bond that was there again, is to take one of the lone pairs that's on the nitrogen and move it into the middle. Okay? So form a bond from it. When I do that, I'm going to draw that over here. That would leave me the lone pair on carbon. I now have 2 bonds between the carbon and the nitrogen. The nitrogen still has 2 lone pairs. And just for aesthetic reasons only, I have moved those so that one is above the nitrogen and 1 is below. There's no reason they have to be moved. It just makes me happier. So this is what I'm looking at here. And I can go through the same formal charge kind of calculation for each of these. And so again, carbon brings 4 electrons to this party. And he has 1, 2, 3, 4, because half of those in the bonds, 4 that he's got there. And that means he has a 0. Cool, awesome. If I look at the nitrogens, all right, he's got 1, 2, so he should have 5. I subtract the 1, 2, 3, 4, 5, 6, and that's a -1. So we still have formal charge. Okay, fine. Now, do I have any reason to think that it doesn't exist like that? Well, actually, yeah, I do. I have reason to think that it's not going to exist like that because I know about electronegativity. Now, we don't do the calculations for electronegativity. We don't do the numerical part of it. But there is a reason that that isn't a happy structure. That charge should be on the carbon because it's an external charge. So it doesn't exist natively. We've added another electron, and we do that by adding it to the species that had the least number of electrons to begin with, which was the carbon. So that charge should be on the carbon. So the way that I can manage that is to take another one of these lone pairs and pull that in here. And that gives me this structure that you're looking at right here. And it didn't draw very well. So carbon, 3 bonds, nitrogen, there's 1 lone pair on the nitrogen, there's 1 lone pair on the carbon, and then we have a negative charge on that. And if we do the formal charge there, I can see for the carbon I have 4 minus half of the 6, so 2, 4, 6, that's the 6 there. So half of that minus the 2, that's a -1 on the carbon. And the nitrogen is the 5 minus half of the 6 that are in the bond minus the 2 in the non-bond, that gives that the 0. And I know that that is the structure that I'm looking for because now I have the negative charge where I think it should be. Okay. Sorry, it was bugging me because it wasn't in the middle. Now, questions about formal charge, how we calculate it, how we assign it, how we look at it. Okay. We're going to talk about it more. So that means that we have our list of rules that we had previously. So up until 5, everything is exactly the same as what we've talked about. So we sum the valence electrons from all the atoms, taking charge into account. We write the symbols for each atom, connect atoms with a bond signaled by a line. Each line is 2 electrons. And complete the octets around all the atoms bonded to the central atom, so everything that's outside. We place any leftover electrons on the central atom. If there are not enough electrons to give the central atom an octet, try multiple bonds. And then check the formal charge of each atom and minimize that formal charge if you can. Best structures have no formal charge, but if negatives exist, they have to be on the most electronegative atom or where it would be put if we were to add a negative charge, okay? So that's the set of rules that I'm going to be using moving forward. Now, I have come back to look at PCl3, right? And the only reason I have come back is to look at what is the formal charge on each of these species, right? So again, here's the math that breaks down the formal charge for each of those. So again, this is the number that are assigned to it. So the number of valence electrons minus half of the bonding electrons minus the non-bonding electrons. But again, we don't necessarily handle it that way every time. The way that I handle it is to say, okay, half of this bond belongs to you, half of that bond belongs to you. So I should have 7, and I have 1, 2, 3, 4, 5, 6, 7. That's 0. Phosphorus and all the chlorines are the same. Phosphorus should have 5. That's how many he brought to this party. He has 2 from there, 1, 2, 3 from there, so that's 5. So that's 0 also. Okay. It's just a slightly faster calculation. All right. Either way is fine. I don't care how you handle that. If the math makes you feel better, good. If it doesn't make you feel better and you want to handle it this way, that's okay too. Really doesn't matter how you get there. Okay. You may be asked to calculate a formal charge for some things, and that may be everything in the molecule, it may be only some things. Depends on the question. Okay. So that's the formal charge on PCl3. We can also talk about formal charge on NH3. Same deal that we've been talking about. So the math that we talk about here, okay, we have 5 electrons that should be assigned to the nitrogen, minus half of the 3 bonds, so 2, 4, 6 electrons in the bonds, minus the 2, and that gives me 0. And again, that's cutting each of those in half. Nitrogen should have 5, and he has 1, 2, 3, 4, 5. And of course, the hydrogen should have 1. I have 1 from that, and that's 0 as well. So same deal. Now, we come back here, and we calculate formal charge here. All right. So if I cut this in half, each of those oxygens is going to be the same. Now, bromine should have 7 electrons. 1, 2, 3, 4, 5. And that gives him plus 2 because he doesn't have enough, so that's a positive 2. Each oxygen should have 6, and he has 2, 4, 6, 7. So each one of them is a -1 charge, and that actually makes sense. The fact that this is a plus 2, this is a -1, this is a -1, this is a -1, 2 of those are going to cancel out, and that'll leave me with the -1 that makes up this charge. That makes total sense to me. But again, I want to minimize that formal charge. And the charge on the Br is positive, which is not necessarily a happy thing. So I want to minimize that formal charge. So how am I going to do that? That's where we need to consider that this is not the best structure. And the way that we deal with that, right? I know that each one of these things has a -1 charge on the oxygens. So I can reduce that by moving one of these lone pairs in here. And I'm only going to do one at this point. Okay, we only do one set at a time. That's all we do. If I do that, that means that this oxygen has not changed. The bromine still has the lone pair that it had. I now have 2 bonds for this oxygen. And then this oxygen has not changed. And that's a -1 charge for the whole thing. Okay, awesome. Well, now I have two different types of oxygen, so I'll need to calculate the formal charge separately for those two types. If I look at my bromine, we have half of each of these. That's 1, 2, 3, 4, 5, 6. Should have 7. Subtracting 6, that gives us a plus 1. Oxygen number 1 should have 6. 2, 4, 5, 6. That's a 0. Oxygen 2, I should have 6, and I have 2, 4, 6, 7. And so there's a negative 1 there. And so again, the overall charge works, but I'm still not minimized on charge. And so I need to do the same thing again to one of the other oxygens. Does it matter which one I do it to? No, of course not. Absolutely not. So this is what one of those looks like, right? And again, I said that that was not entirely happy. So we'll move one more, okay? And if we do the formal charge here and look at our bromine, should be 7. And I have 1, 2, 3, 4, 5, 6, 7. And we'll label this one as 1, and this one as 2. And of course, this is a 1 also. 2, 4, 5, 6, 0. And O2, I'm going to have 6 minus 7 is minus 1. Oh, awesome. That's exactly what it should be. All right. So from a formal charge perspective, this is exactly what we need. I'm going to ask you, once I've taken some of my drawing away, is there any reason that I would think that in reality, those oxygens would be any different from each other? The answer is either yes or no. And the answer to me is no. I would expect, excuse me, that within this structure, all of those oxygens should actually be the same. So how does that happen? Well, it happens through a thing called resonance, right? So we want it to be 0 on all of the atoms. We keep moving until we have as few charges as possible, which we've done. All of those things we've taken care of. But we can't do this, right? If I try and make them all exactly the same, that formal charge is not the way it should be, because now the charge is on bromine, and that's not what I want. Okay, it should be on oxygen because he's higher up, so it should be on him. So that's not a good thing. So the structure on the slide previous, this one right here, is the right answer. But that's weird because they're not all the same. So again, the way that we deal with that is something called resonance. Okay, I know that in reality, this is a very fast moving thing where the electrons are all over the place. Right? They keep moving. So they actually exist in between any of those oxygens and the bromines. And there's no way really to tell the difference. If I were to look at this thing and label those oxygens in such a way that I can tell them apart, which we can do in the lab, okay, what we see over time is that this actually ends up being more like 1.5 bonds for each oxygen. And so on paper, there's no way for me to draw that very well. It's complicated to draw on paper. And so we typically draw that by moving those bonds. So I have a structure here where I have 2 double bonds at the bottom, a structure here where there's 1 double bond at the bottom and 1 up here at the top, and over here where I have 1 at the top and 1 on the other side at the bottom. So I've shown all 3 structures that show the double bonds where they can be. Okay, that's a resonance structure. That is required to completely show what that thing would look like if we actually had it. There's one other thing that I can do. It's not going to be big enough. And I'll explain this in just a second. This whole thing is a -1 charge still, but you'll see that I have one bond and then this dotted line. And that's another way that we can draw that 1.5 bonds that exist, indicating that that is fluid between those three positions. It's just another way for us to represent that on a piece of paper. That's all it means. And that's the best representation that we can get of what actually exists in nature. Okay? So, does resonance exist? Yes, absolutely it does. Will I ask you what resonance is? Yes, in a way. I don't think that I will ever ask you to draw all of the resonance structures. If you need to be able to draw a resonance structure, guess what? You get to take organic and you'll do it all over the place. That's a lot of what gets done in that course. But you may get asked, what does resonance mean? And resonance just means that there are multiple places where the electrons can exist. That's a definition that can be used for that. So electrons can exist in more than one place. All places are equivalent. Okay, so that's what that means. We have questions about resonance. Okay. Actually, I'm going to skip that one. Because we actually talked about that. Now, one other thing that I have to talk about. I really do have to talk about this part. And that is, we don't always have an octet. It's not always possible to make an octet. And that's not just for things like hydrogen and helium. Hydrogen and helium don't have an octet. They have a duet, and that's because they only have space for 2 electrons. But we also have situations where there aren't enough electrons to make everybody happy. So if we look at NO, right? Nitrogen brings 5 electrons to this party. Oxygen brings 6 electrons. It gives me a total of 11. There's no way I can get an octet out of 11. It's just not going to happen. Okay? The best structure that I can make is this one, where I have 2 lone pairs on the oxygen, 2 bonds, so there are 4 electrons in between them. So 2 of those go to this oxygen, which means that the oxygen has no formal charge. Then the nitrogen has 1, 2, 3, 4, 5 electrons assigned to it, so it also has no formal charge. But this nitrogen does not have an octet. That is a violation of the octet rule, and that happens. Okay, much as we would love to say that it's always a perfect octet, that is not the case. So we do get violations. Odd numbers of electrons are really common for that. Now, if I have 2 nitrogens, that problem goes away, but it doesn't always happen. Okay? We also have some things where there just aren't enough electrons. Now, you see this structure over here. So this structure is obviously made from 2 molecules. It is BF3 and NH3. We drew the structure for NH3 previously. And that structure for NH3, if you remember, looked like this. And there was a lone pair on that nitrogen. If I draw the one for BF3, boron has 3 electrons that he brings to this. Each fluorine has 7. 3 there, 21 there, 24 total. I do 2, 4, 6 in the bonds. Yes, I can't do math. Okay, just making sure I was not being ridiculous. And then 2, 4, 6 there. And I have to do that for all 3 of those. And of course, 6 times 3 is 18. So I have no electrons left, and B is left with only 6 electrons around it. That happens. Okay, there are no more electrons that I can do with this. We're not going to make a double bond. And the reason that we don't make a double bond there is because we can't. Because B and F, both of them are in the second row, that's not possible there. So we don't make a double bond there. So we're deficient in our octet on the boron. But if a BF3 and an NH3 happen to be in the same beaker, then the nitrogen has that lone pair and the boron is missing some, so they can share. And they do. And that's called a polar covalent bond because both of those electrons are being donated from one species. So that's this bond right here. It's called a polar covalent bond. So it's covalent, meaning they're sharing it. Polar because it's all been given by one species. Okay? So that is something that you can see. I will tell you right now, I absolutely love this structure. I think it's an awesome structure. It's a way for us to draw a Lewis structure for something that has an octet, something that doesn't have an octet, a way to show that they can share those things. So you may see this. Okay? You may or may not, but you know, it is one of those things that I like to ask about. So that is something. Are there any questions about that? And that's not the only type of exceptions to the octet rule, because I mean, it's just a general idea, really. It's not a hard and fast rule. We also have things like PF5. So molecules that have more than an octet around the central atom. This happens. PF5, if we were to draw that, 5 bonds implies 10 electrons around that phosphorus, which there are. That's more than octet. So that is a violation of the octet rule. Okay. Now, since P is in row 3, he can do this. Okay. So he's capable of doing it. This is a perfectly acceptable structure. And we draw this structure in the exact same way that we've done previously. We know that phosphorus brings 5 electrons to this. Each fluorine brings 7. There are 7 times 5 is 35. Plus the 5 is 40. We then draw all our bonds, 2, 4, 2, 4, 6, 8, 10. So that's 30 left. 2, 4, 6. 6 times 5 is 30. So yay, I have now taken care of all of them. Oh, I'm sorry. Shut down on me, I apologize. So that is another place where we violate the octet. So we have additional electrons around that central atom beyond the 8 that we were expecting. Okay. So that is a violation of the octet rule. Anytime that we don't have 8 around my central atom, that is a violation of the octet rule. Hooray for technology. Okay. Connecting. Hooray! And here is where it will become obvious that I have a major fascination with water. Water is a really, really interesting structure. It's very different than a lot of things that we know, and it's what makes a lot of what we see in nature possible. If we draw a Lewis dot structure for water, we know that we have that hydrogen that's bonded to the oxygen, and then the oxygen is bound to another hydrogen. So that takes up 4 of the electrons that are present for that. We have 2 lone pairs that exist on this oxygen. For reasons that we will talk about in the next lecture, those lone pairs exist on one side of that particular atom. And I know that oxygen is more electronegative than hydrogen. And because of that, he's going to pull more on those electrons than the hydrogen does. So even though these electrons are shared in this bond, they spend more time with the oxygen than they do with the hydrogen. It's not an equal sharing. Okay, it's like an 80-20 split with parents. So 80% of the time one parent, 20 the other. Okay, that means that this molecule has a net negative charge on this side and a net positive charge on this side. Okay, and we can see that by looking at electron density map. Okay, high concentration of electrons here in the red and low concentration out here on my hydrogens. Okay? So that means that I have an unequal sharing. Now, that partial charge is part of why we see some of the things that we see. Okay? So that's an interesting thing for that. Electron density on one side of that molecule is much higher than the other side. That's a polar bond to indicate the electrons are not evenly shared. Leads to an ease in dissolving salts. So again, if I have a sodium chloride, it's made from an NaCl. And if I put that into water, the attraction between the sodium and the chlorine becomes very small comparative to the attraction between the Na and the oxygen side of these waters. And what we end up having happen is that we get a cage of the oxygen ends forming around that Na plus and a cage of the hydrogen ends forming around that Cl minus. And that's how things become aqueous, because they get additional stability from hanging out with that polar molecule. Okay? So that's very interesting for us. And that's one of the reasons that we can dissolve some of the things that we can dissolve. Now, does it work for everything? No, not for everything. It depends on how polar that particular structure is and where the electrons live in that structure. That's not something we're really going to talk about, but that's why some things dissolve and not everything does. Okay. And again, remember that we know that it's not equally shared because of the electronegativity. Okay. Questions about that? Now, again, you may, if you look in your textbook or if you look this up on the internet or any of that stuff, we're not going to do the things that the math parts of this. We're only doing the qualitative side of this. Okay, you can do the energy calculations. It's called the dipole moment. That's not what we're going to calculate. Okay, but we want to talk about the difference in a qualitative sense about what this looks like. So I've drawn 2 structures here. So I have one for CO2 and one for H2O. Okay. And remember, we have our carbon. There are 4 electrons that are shared in these double bonds. I have 2 lone pairs on each oxygen, 2 lone pairs on these oxygens, and the 4 in that bond. And then I have 1 bond here, 1 bond here, and 2 sets of lone pairs on that oxygen. And I say, notice anything? Because I do. All right. The electron density on water is all on one end of that molecule. We just talked about that. So it's all up like this. And that's the structure that you actually see, right? But the CO2, if I look at that, there's equal pull in both directions. So even though the electrons spend more time with the oxygen than they do with the carbon, they're on opposite sides of the molecule. So there's equal pull in both directions. So there's no net pull in one direction. So we don't have that partial negative and partial positive. So this thing right here is said to have a dipole moment. And that's because it has a partial negative charge on one end and a partial positive charge on the other end. This one, on the other hand, has no such charge separation and therefore does not have a dipole. Okay? And like I said, we're not going to calculate the actual values for this, but I am going to ask you after we look at the three-dimensional structures in the next lecture to decide if it will have a net dipole, because that we can do. All right. So questions about that, knowing that there's more to come on that topic. Okay, well, what if we make two bonds, share 4 electrons between C and O? That we just did that. Okay, fine. When we talk about nitrogen, okay, we we have nitrogen. Each one has 5. There are 2 of them because I know it's an N2 in nature, so that's a total of 10 electrons. I can do 1 bond in between them. That takes up 2 of them. That leaves me with 8 that I need to distribute. And I can go 1, 2, 3, 4, 5, 6, 7, 8. Okay. But if I do that, then I have 1, 2, 3, 4, 5 on each. Neither one of them has an octet. That's not a great structure, right? So I can change this and I can move one of these in here. And that gives me a structure that looks like this one. And I've moved that one lone pair down just to make it more obvious. Okay. Again, this is not necessarily the best structure because if I look at my formal charge on this nitrogen, it should have 5. It only has 1, 2, 3, 4 that are assigned to it, so that's a +1. And if I look at this one, it should have 5. It has 6 that are associated with it, 2, 4, 6. So that's a -1. Again, not happy. So I can take and make another double bond, which is how I get to that structure right there. And that's a triple bond. Okay. So double bonds and triple bonds. Okay. Double bonds share 4 electrons, but notice they're all in the same space, right? So even though from an OChem perspective, they're not exactly in the same space, they're not. I mean, from a 3-dimensional perspective, they're not. But they're shared between the 2 atoms, okay? Then we consider them as one bond. Okay, this will be important when we talk about the structures next time. Multiple bonds are considered as if they are a single bond when we start talking about 3-dimensional structures. Okay, and that's because they exist in that same physical space. Okay, so questions about that? All right. So that brings us to the end of this part, drawing the Lewis dot structures for each of these things to determine how many bonds and how many lone pairs are present. Okay? That is what we're going to need to deal with there. We are going to be using this exact information to deal with our next lecture. So when we talk about the next thing, which is called VSEPR, it's valence shell electron pair repulsion, we will need to have a Lewis structure to be able to do the VSEPR. Okay, so we're not going away from this. We're absolutely going to need this. And so practice, lots and lots of practice in setting these up. Okay, now I'm willing to hang out and do any of the in-class practice, talk through any questions that anybody has. That's perfectly fine. I have office hours until between 10 and 11 anyway, so I will be here until 11. But that is all I wanted to talk about today. So does anybody have any questions? And I know that I got a comment about the post lab for the stoichiometry having some issues. I'm going to take a look at that today and see what's going on. So I will take a look at that.
Good morning. Can you hear me? Hello? Uh-oh.
I don't think she can hear us.
Oh, I don't know what's going on.
Actually, Alicia, I can't hear you. I saw your chat, but I can't hear you. Give me
Yeah.
2 seconds. Let me adjust my sound.
I told her that you were talking as well in the chat.
I'm not hearing anything. That sucks. Yeah, I am not hearing anything. It's so bizarre. Why are you being... Okay, that may help. I don't know.
Okay, what about now? Can you hear me now?
Yeah, no, still nothing. It's bizarre. Tell you what, I'm gonna leave and come back and see if that helps. I'll be right back. There we go. Now can you hear me?
Now I can hear you. Can you hear me?
I can, yes.
I don't know if Yash is coming back. I thought he was gonna leave and come back, but I think he had to go. Um, I I don't know why I'm not doing good on the Alex assignments. That has really like hurt my grade a lot, and I don't understand. I don't know why when I get to Alex, they're so much harder than the practice sheets. I don't, it's really I'm really struggling with Alex. And I remember we talked about you giving me more time on
Yes.
the assignments. But I don't know why that didn't register to me to go. I don't know. I didn't go when I looked at it last night, and I also had some issues with the one for stoichiometry as well. When I would go to the question, go to the next question, and then come back, like on the last two, I think of question 4 and 5, the questions like disappeared,
See,
and
that's
all
what's
I had
yeah,
was the
that's
formula.
that's what somebody else was saying. That's so bizarre. I really don't I don't know. So I'll have to take a look at that because if you can't see them, you can't be expected to answer them.
And then
So,
I got a 42 on it, and I was like, I thought I knew what I was. I don't know. The Alex work is so much harder than what me and you go over together, and I don't know if it's because I'm not putting the sig figs or if I'm just not, because sometimes it doesn't like certain answers that you put. So I'm not sure. I'm not sure how to handle that, because that's what's really um hurting my grade right now is the Alex. And I know you said, oh, if you don't do your Alex, of course, you won't be able to pass the class, but I don't want that to be the reason why I don't pass the class.
I'm trying to take a look.
Okay.
So it does seem like there's still some things that haven't been turned in for Alex. There are some things where not all of them were scored, and let me see what it says about.
Then I got 10% on some things, and I'm like, what? How did I get a 10 on this? I'm just not sure. It doesn't even show you like what you got wrong. It says like have another attempt, but I'm like, I don't know where I went wrong. Are
Yeah.
these quizzes?
So the post labs are considered quizzes. Yes, they are.
Okay, I thought they were just like homework, considered as homework.
Well, so the post lab is, I mean, it's not necessarily a quiz. We have to set them up as a quiz. That's the only way that we can set them up in here. But they're not really a quiz. It's really meant to be like, they used to be worksheets that were given after each lab to ask you about stuff that was done in the lab.
Okay.
So if there are things that you didn't get the first time, that's something you should be able to ask about, and then go back and do better, because it should only show you the questions that you missed if you do it again. That's
o-
how that's how it's supposed to get set up. But we can talk about that in just a second.
Okay.
Oh, it was this one. Yeah, okay.
I don't know. I thought I did something wrong, and then they just
On
like went away. I don't know.
on which part?
On I think questions 4 and 5. It was only two questions that the last part disappeared, and I didn't know what happened.
And I really don't understand why that disappeared.
Like once I put in my answer for the top one, like once I typed in my answer, it disappeared from the bottom. And I don't even know. Yeah, I don't know what I
Hooray!
did wrong. And then when I got to the next question, it did it again. And I was like, I don't know. I don't know what happened.
Again, I can take a look at that. I can see from looking at the stoichiometry question 4, the first one, it didn't like your sig figs. That's the issue that's happening there.
Okay. How I wasn't sure how to determine how many to there.
Well, so the number that they gave you is 1.42. So
Mm-hmm.
that's 3 significant digits. That's what they were looking for.
I think I only put two.
On the first one, it's more than that. So it was 3.0982, which would round to 3.10, which is the answer that they're looking for. But
Oh,
but yeah, I mean, that's a sig fig issue. And I mean, yes, it's going to score it wrong, but that doesn't necessarily mean, these are things that I can go back and, if it's just a sig fig issue, we can deal with that. That's because as far as I'm concerned, if it's not going to be consistent about it, then that's a problem. And really, it's not. Sometimes it does it the way I think it should. Sometimes it doesn't, and there's no rhyme or reason for what it seems to be doing.
okay.
So that I can take a look at, and that I can go through each one and see if that, if that's the only thing, if it's only the sig figs, we can talk about that. As far as other stuff, what I can do today is take a look and see if there are any things that I'm noticing in terms of like, patterns that are happening, things that are being missed, things that don't seem to be understood, and then I can send you an email about it and we can talk about it tomorrow.
Okay.
Does that sound okay?
Yes. That sounds good.
Okay, because again, the Alex is important, but
Very, yeah, I know.
it's more important that you understand what's going on. And I'm still looking at the tests, so it's one of those things where if I feel like you did well on the test and the Alex wasn't great, then I am inclined to go back and give you additional points on the Alex, and I've done that before, because the tool should not be a hindrance to your grade.
Okay.
So I think that's probably the best thing I can do, because it's going to take me a little while to look through all of these to see what's going on.
I
As far
understand.
as far as the things disappearing in the stoichiometry, I don't know what's going on with that. So those questions will probably end up getting thrown out. But you were asked to turn in the actual piece of paper for that. So there's a Dropbox in the D2L for the paper that goes with that.
Oh, the scratch work. Okay.
Right. Yes. So there was a paper version of it that was supposed to get turned in. So I should still be able to grade that, even though the Alex is freaking out.
Okay, then I'll have to submit that. I did not submit my scratch work. But
And
it's
that's okay. I will remind people that they need to do that. So yeah, that is something that I need to see.
okay.
Okay.
And then I think he's back, so I'll let him ask you a few
Okay.
questions.
Hey Yash, what's up?
Hey, I had a quick question. Are you
Yes.
available after like my second class? Like
Yeah.
around, yeah. Okay.
Yeah. I'll be here. Yep.
Okay, thanks.
Yeah.
We had the lecture quiz and we were on aqueous solutions, and for my lecture quiz for that one, I just put that I was still having a hard time with balancing.
Right.
So and then once we included the aqueous solutions, it got even harder. So I wanted to get some help on the first couple lectures, like do a couple problems from them, and then of course like we did for the first exam, I'll go back and work on
Okay.
the sheets.
So do you have any specific ones that you want to talk about, or?
I am looking right now. So we had the ones on balancing. Okay. So it says balancing net ionic equations. I wanted to go through a couple of these.
Okay. And these are the in-class practice sheets for them?
Yes, ma'am, for lecture 7.
Okay. All right. So which ones do you want to go through?
Okay, so the first one, why is it not letting me split my screen? Hold on one second. I'm trying to. And then on Friday, I couldn't hear anything, so I had to leave the lecture. I remember I sent you a chat, and
Yeah.
when I tried to come back, I still couldn't hear, and I wasn't sure what was going. It might have been my internet. I wasn't sure. That was the first time I ever had problems with not being able to hear anything.
I,
But
I I didn't get any reports that was going on for other people. So
so that's why I think it was my internet.
yeah, I mean, because it was a different setup, so there may have been something with it, but I don't know. I mean, and I can review the lecture recording and see if there's anything going on in there. But we can talk through what we talked about on Friday if you want.
Okay. I just wasn't sure what was going on. And my brother, he's a streamer, so sometimes he like messes with the internet late at night when I'm like not up. So I wasn't sure if he had the extender connected to the internet or whatever, but I could not.
Right.
It was lagging and I just couldn't hear anything. But the first one has bromine plus sodium oxide, and that yields to, I don't even know how to say that. I never know how to say these names. NABR.
Sodium bromide, yes, NABR.
I never know how to say those.
That's all right. You can just say the formula. It's okay.
Okay. And then iodide.
Yes.
Okay, so it says write the total net ionic equation for each of the following. Okay.
So
Um,
when they say total net ionic, what they mean is all of the ions. So
okay.
there are three different types of equations that we write when we talk about this. One is a molecular, which is what we're looking at right here. This is considered a molecular because it shows everything as if they were molecules. So I know that these aqueous things, even though they're in water, they don't stay as NaI, but that's where they came from. So it's written that way.
Okay.
But when they get into solution, we end up with the Br2 staying together. And then I have the Na plus and the I minus. And of course, that's going to go to Na plus on the other side. And a Br minus, because both of those are aqueous. And then the I2, which is a solid. So the I2 stays as a solid. The Br2 is still a liquid. So those two stay together. They don't come apart. But anything that's aqueous is going to come apart. And that's going to show the ions for that. So that's where we get this Na plus and the I minus, because the cation comes apart from the anion in water.
Okay. Mhm. And then it says to balance it, and this is clearly not balanced. Well, the sodium is balanced, but bromine is not because we have 2 on the reactant side
Right?
and 1 on the product side.
Okay. So how are you going to fix that?
Um, Let me write it down. So, and then we have 1 and 1, and then 2 and 2. So I could just put a 2 in front of the bromine on the product side.
Well, okay. We're going to have to balance in the molecular part. And then whatever we do in the molecular is going to have to be reflected in the total ionic. So if you're looking at your Br2 liquid plus NaI aqueous going to NaBr aqueous plus I2 solid, that's the one you need to balance.
Okay. So I wouldn't put, all right.
I would do it here first, and then we'll worry about what happens here.
Okay. Mhm.
Because you still have the same problem, right? You have Br2 on this side and one Br on this side, on the product side. So we still have the same problem we have to fix.
Could I just put subscript 2 for BR?
Now, we can never do it with the subscripts. Remember, the subscripts are determined by the charges.
The
So
charge.
since this is an Na plus and this is a Br minus, they have to be NaBr. So the only way I can balance is the number out in front of it.
Okay. Then that gives me, that balances out the bromine, but it doesn't balance out the sodium on the reactant side. So But then that'll make, if I take another 2 and put it in front of sodium iodide, then that's going to make 2. Oh, then that'll be 2 and 2.
Yes, that's exactly right. And then whatever you've done there, you have to carry that down here. So that becomes a 2, that becomes a 2, that becomes a 2, and that becomes a 2. Because those came from here. So if there were 2 NAs here, there are 2 NAs here. There are 2 BRs here, there are 2 BRs here.
Okay, so you balance it in the molecular and then you bring it down to the ion
Correct.
to
That
make
is
it
correct.
a
Yes.
little easier. Okay. So number 2 is carbon oxo.
That's calcium hydroxide.
Oh, calcium. I'm sorry.
That's all right.
Calcium hydroxide. Hydrogen chloride.
It's also known as hydrochloric acid. Yes.
And calcium chloride.
Yes.
And then water. Okay. Well, I know that calcium is a alkaline earth metal, so that charge is +2.
That's correct.
But it has to stay with this how do you say it?
Hydroxide is that one.
Hydroxide. It has
Yes.
to stay with this one. And this also has a charge of 2.
It's a 1 minus. Each one is a 1 minus, but there are 2 of them. So yes, that is true.
But then I would put it, this needs a negative here, right?
No.
Okay.
So this is balanced for the molecule. Everything is balanced for the molecules that are here, but we may not be balanced for the number of them. So when I do this, I would say Ca, O, H, and Cl. And I worry about the Cas first because they're not O and H. Then I worry about the chlorines. There's 1 there and 2 there, and I see that that's a problem. So since I have a problem with the chlorines, I'm going to go ahead and fix the chlorines on the reactant side.
Okay. By putting a 2 in front
Correct.
of
And
hydrogen.
then I look at, okay, so I have 2 oxygens from the hydroxide here, and I have 2 hydrogens from the hydrochloric acid and 2 from the hydroxide. That's a total of 4. On my product side, I have 2 hydrogens and 1 oxygen. So obviously there's an issue there.
Mm-hmm. Um, well, no, I don't want to do that. Because the only thing left to do on the reactant side is put a 2 in front of the calcium
Hydroxide.
hydroxide, but then that would make 2 calciums on my
But
reactant.
if I look at what I have here on my reactant side versus my product side,
Mm-hmm.
I see that the problem that I have is with oxygen and hydrogen, right?
Mm-hmm.
So I need to deal with both oxygen and hydrogen. And I need more on my product side than I currently have. Because I have a 1 and a 2 on my product side and a 2 and a 4 on my reactant side.
Oh, we'll just put the 2 in front of water.
Yes. And then you're good. So that's your balanced molecular equation. Erase that because it gets in my way. Now we want to talk about what do the ions look like. So anything that's aqueous is going to become ions. And like you said, we know that Ca is a 2 plus. So that's a Ca2 plus, and he's aqueous. I know that I have hydroxide, and hydroxide is an OH minus. That's the polyatomic ion, and there are 2 of them. So that looks like that. Because the ion itself is the OH minus. The 2 of them goes out in front because we're not balancing for charge here. So that has to go out in front.
Okay.
We do the same thing with our hydrochloric acid. So what's the cation on the hydrochloric acid? What's the part that's positive?
The chlorine has a charge of +2.
Oh no. So remember, chlorine is always a -1. So I know there are going to be 2 of those, and it's a -1. And that's aqueous. And that means that the positive part is the other part, the only other thing that's left. And that's 2H plus. And that's aqueous as well. And again, chlorine is -1 because he's a halogen. So he needs to pick up 1 electron to be like the nearest noble gas.
Okay, I got that written wrong. I have for my chalcogens, I have -1, and then
So halogens, those are the -1s. Chalcogens are -2. So the oxygen down, those are the chalcogens. Those are -2.
well, I know I messed up something on my test. I had that confused. I know I messed something up there. Because I just wrote it the same way I wrote the alkaline earth metals, like they're charged down here. I wrote +1, +2, and then when I got here, I wrote -1, -2.
Yeah, it's the opposite order. And that's because of how close it is to the noble gases. So the halogens are 1 away, the oxygens are 2 away. So that's why they're -1 and -2.
Okay. That fixed now.
So that's that half. Now, when we go the other side, we have to deal with the CaCl2 because that's aqueous too. So when I take that apart, what's the charge on Ca?
2 plus.
Right. And he's aqueous.
And
And
then
then what's the charge on Cl?
-1, so we would have 2 Cl minus.
Yep.
Okay.
And then the waters, because they're liquids, stay together. They only come apart if they're aqueous.
Okay.
So this is my molecular. This is a total ionic. The other thing that we occasionally write is called a net ionic. And in the net ionic, what we're going to do is ignore anything that doesn't change. So you see this Ca2 plus is aqueous here. Ca2 plus is aqueous here. It didn't do anything. So it's just standing around. So we can ignore that.
Okay.
The chlorines, I have 2 chlorines here, 2 chlorines there. They didn't do anything. So I can ignore that. And so the only things I'm concerned about in my net ionic equation are the 2 OH minus plus the 2H plus, going to give me 2H2O liquid. Now, a couple of things. Some people will write this as H plus first, then OH minus. Whether you do or not is fine. Some people insist on dividing all of this by 2 because it's all divisible by 2. That is fine. You don't have to. It's okay if you do. It's not required.
Okay, so then I could just leave it like this.
Yes. Yes.
Okay. Okay. All right. Um, mhm. Okay. The next one says identify which ones are aqueous or not, and then balance the total net ionic equation. So that would be that second part that we did where if it doesn't change from
Correct.
we would just
Correct.
okay.
And then we have to decide so one, what our products are, and two, if any of them are insoluble.
Okay.
So the first thing we're going to worry about is what are my products? So how do I determine what my products
I don't remember. I do not
are?
remember.
We're going to square dance and we're going to change partners. So the cation on the first one, the Ag plus, instead of being with NO3 minus, is then going to be with the Br minus. So I start with this AgNO3, and that's aqueous. KBr, and that's aqueous. And I'll show you how I know that those two are aqueous, but trust me, they are. And then I'm going to make AgBr, and they actually have told me that, and KNO3. So those are my products. So they told me what my products were. Well, yay. That's awesome. Then I need to look at my solubility rules from the exam handouts.
Mm-hmm.
And in my solubility rules, I can see it says so common salts of group 1 elements, and K is a group 1, are soluble. So KBr is soluble, and KNO3 is soluble. So AgNO3 is soluble. No, that's KNO3. Sorry, wrote it wrong. Oops. So that's soluble. So the KBr and the KNO3 are both soluble because of that first rule. It says all common nitrates, which is this NO3 minus, are soluble. And that's how I know that the AgNO3 is soluble. Okay. So that's 3 of my things. So I know if there's going to be a solid, it has to be the AgBr. But I don't know if it is a solid or not. So if I come down and look at rule 3, it says most chlorides, bromides, and iodides are soluble except silver. So silver is a solid. So this one right here is a solid.
Okay.
Now I need to make sure that everything's balanced. Does it look like everything is balanced?
1 second. Oh, golly. So, silver 1 and 1, nitrogen 1 and 1, oxygen 3 and 3. Oh, this one actually is balanced. Okay.
Yes, it is. So that part's fun and easy. Now we need to break all of the aqueous stuff down into the ions that it's made from.
Okay.
So what are the ions that are in AgNO3?
Ag is well, Ag is in that D block, so just +1.
It is just +1. And I know that because NO3 is -1. Nitrate is in that list of common polyatomic ions. And so if NO3 is a -1, then Ag has to be a +1 because there's one of each of them.
Okay. So I would have AG is +1, and then NO3 is just -1.
Yep.
That whole thing is -1, and there's only 1. And then potassium is +1, and then bromine is -1. Okay.
Right. And then so what do I do with that solid?
You just leave.
Yep, correct. And then what about that other product that I've got?
I have potassium at +1 and NOO3 at -1.
Right.
And then when I look at it, well, my NO3 did not change.
Correct.
With that, my potassium did not change.
Correct.
So I would have, I guess my AG and my bromine aren't any different either, because on this solid it's still the same. Because they're separate, I have to write them out.
Well, since I made a solid, it's
Mhm.
no longer just an aqueous component, it's changed phase. So that's what we're looking at.
Okay. So then I would have AG plus UG. Would I not bring my... Oh, okay. I was just about to ask that.
I was waiting for you to say it.
I was about to ask, would I just
Yep.
leave it there?
Nope. We need to have that too. So anything that changes phase, that's what we're typically looking at. So anything that becomes a solid, anything that becomes a liquid, anything that's gone from aqueous to something else, that's what we're going to be writing the ionic equations for.
Okay. Number 5. Nickel. Solid plus you know 3 to yield 9. Lead. Okay. Well, I already know that nickel is a solid. Now I need to see if lead NO3 is aqueous. All common nitrates are solid.
Correct.
So this is aqueous.
Correct.
PbNO3 is aqueous. And nickel NO3 will be aqueous on the product side now. And I
Correct.
know that lead is a solid. Ni would just be well, this one is negative. The lead NO3 is negative. So this one will be +1, the nickel.
Well, no. And so I know the NO3 is -1, but there are two of them.
Oh, 2 NO3.
Yes. And that's the same on both sides. So I know that PB is +2 and
Mhm.
NI is +2.
2 3 minus. And why are they +2? Looking at the periodic table.
Well, so they can be many things. PB and NI are both in the D block. So they
Right.
can be many things. They are what they are because I know that NO3 is a -1 and there are 2 of them.
So I have to have 2 positives to.
Correct.
Okay.
Yep.
Mm.
And so if I was to do the total ionic equation, I would show the PB2 plus as aqueous and the 2 NO3 minus aqueous. But the nickel is still solid. And then on my product side, I have nickel 2 plus aqueous plus 2 NO3 minus, which is aqueous, plus PB. So I've taken all of that aqueous stuff and taken it apart.
Okay. Oh, I didn't even see if it was balanced before we did that part. I should have done that first.
Oh, we should have. But go ahead.
Okay. Because now it's going to be harder for me down here. I'm going to go back up to the top.
And that's fine. That's what I would tell you to do. So
Point one. One oxygen, 3 and 3. Okay, this one is already balanced. Oh no. Oh yes, it is.
yes, it is.
Okay. 1 and 1, 1 and 1, 1 and 1, and 3 and 3. Okay. So then, when I go to write my net ionic, 2 NO3 minus would be gone.
Yes.
And that would be it.
Correct.
So I would have Ni plus PB 2 plus U Ni 2 plus PB.
Hooray.
No, this is hard. This is a little. I think the hardest part is gonna be um figuring out my charges for my ionic or for the total ionic equation.
Yeah. I mean, and again, if you have a molecule like PbNO3, I know that NO3 is a -1. So that gives me a total -2 charge. So PB has to be +2. We call that determining charge by inspection.
Okay. Okay.
And that may be, I mean, a lot of times that's what I do as opposed to actually like looking at the table if if I can. But like I know like I know all the halogens, I know oxygen. So a
Mhm.
lot of other things I just go, okay, if Ca is with O and it's 1 to 1, then Ca has to be 2 plus. You know, that kind of thing.
Okay. Um, I know you're about to get off here at 11. I don't go into work until it was supposed to be 2:30 or 2 o'clock, but she hasn't changed it yet, so I don't go in until 2:30. But um, are you gonna be back on after 11? So I
Uh,
remember you asked if you would
So
be.
yeah, I'm I have office hours until 11.
Mhm.
And then normally Josh comes by. It depends. But I leave at 3. So I mean he's usually here after his second class.
Mhm.
So I'm fairly sure that I could pop into the WebEx as soon as I'm done eating lunch, and then you can, if I'm here, I can send you an email.
Okay. All right. 'Cause I still have lots of questions.
Sure.
Especially with the Alex. I don't want to get. I know there's stuff that's due tonight at midnight that I'm not even sure I'm gonna do too well on.
Are you talking about post lab stuff?
I'm not sure if I'm gonna do too good on those. But I don't even know which ones are due. Let me see if I can get it. It always logs me out. I don't know.
Oh, it's very good at that. Yes.
Then I have to go back into D2L because I don't even know my like actual Alex login. I just go through the portal. Um, okay.
Uh,
So we have a post lab on synthesis due tonight at midnight, and we have a post lab on synthesis of calcium carbonate that's due tomorrow night at midnight. Um,
Well, one of them should be the lab itself. Give me a second. Let me look at my actual assignment list.
see, though, I haven't done actual labs since the first week of class. Everything else has been the quizzes.
Well, see, that would be why you can't do well on the quizzes because they're all based on the labs.
Assignment was not taken, assignment was not taken, assignment was not taken. See, all these say homework, and I did the virtual labs that were available. I don't know.
So there are a bunch of labs. Let's see. We're
Set up, I
currently
don't.
at density of a cube was 5. Synthesis of calcium carbonate is virtual lab 6, and that is due on the 4th. So the only thing that's actually due tonight is the post lab for. Wait, that should not be due tonight. It should be due tomorrow. And that should not be due. Hold on. That should not be. The only thing that should be due tonight is the stoichiometry. The post lab of the stoichiometry.
Because I did the tutorial, I did the one with the graduated cylinder, I did that one. And then I started the one with density of a cube. And I think there was like one part that I couldn't get it right, and I just didn't submit that attempt. But I had progress in that one. I meant to ask you about that one, and then I had forgotten to ask you about it. But I did that one, and I don't know like why when I took the quiz I got a 10%. I didn't understand where I went wrong with that one. Um, I don't know where.
Let's see. Let me see what I can see. Post lab density.
And post lab skills, I got a 17. I'm like, I don't know, I don't know what I'm doing to get these grades. because I'm putting in the study hours. When I get on here with you, I and I'm understanding when we're doing it together, and then I'm not sure where I'm going wrong with the Alex.
Well, and again, I mean,
So
looking,
tonight I need to do the lab for calcium carbonate, and then I will be able to do the post lab since.
so the post lab for calcium carbonate should actually be due a week from tomorrow because the virtual lab 6 is supposed to be done tomorrow. 4/4.
Virtual lab 6. Oh, I don't know. I don't know if I can't find. Okay, I'm gonna share my screen with you. I can't even find these. And I know you gave us a tutorial on Alex and everything. So this is my screen. Okay. So this is my screen.
So synthesis of calcium carbonate, virtual lab 6.
Mhm.
It's right. Hold on, you keep going past it. Right there.
Yep.
That is due 4/4. That's due tomorrow.
Right. Okay, that's what I was saying. I need to do this in order to do.
The post lab, which is due next week.
Okay. So the post lab synthesis.
That's the one that's due today.
Where's the lab for it? The actual lab, the virtual lab. See, mine has homework, homework, homework.
See, post lab synthesis is the synthesis of calcium carbonate, and that's due 4/11. Refresh your screen.
Okay. So I know I did the virtual lab for density, and then I took the quiz. I did the lab, and I did.
The quiz had 2 parts, and part of it you missed, and that's why it gave the score that it gave. So 1, that's part of it. The other part of it is because it was turned in late. So that's why the score is what it currently is. So there are 5 questions, one of which you got part of it right, one of which was not correct. Yeah, okay. So part 4 was not correct on that. The other parts were sig fig issues. 3 was right. 4, sig fig. That one's right. That one's right. That one's... So normally when there's an issue with the sig figs, it normally comes up and says that check your sig figs. And what I tell people, and it's a stupid thing to say, but is if it says check your sig figs, although it's not going to do that on a quiz, but I can go back and adjust these grades. I just haven't had time to go back and look at all of them yet.
Okay.
Because it looks like the majority of these are sig fig issues. And I mean, there's one that wasn't calculated. Well, no, that is a sig fig issue. That is a sig. No. There's one of them that Yeah, part 4 on number 2, that's not a sig fig issue.
I just got that entire question wrong. But that was the one, that was the part on the actual virtual lab that I was struggling with.
So let's go talk about the virtual lab and see what's going on for you there. Because I can't see that since you haven't submitted it.
Okay. I don't even think I can get into it.
You should be able to.
Mm. You know what? It's Safari. Alex does not like Safari. I don't know
No,
why.
it does not.
I don't know why it doesn't. So I have
But
to,
according to their specifications, it is not compatible with Safari.
so I have to go in here. Okay. Maybe that's why my quiz, the Stoic quiz, gave me.
And that may be, yes.
Maybe me and someone else forgot to change our browser. Always forget to do that. Okay. Oh, it didn't save my progress. Oh, it didn't save the progress. It wasn't this one. I had issues at the part where it's asking me to calculate the calculate the mass of the item that I put into the graduated cylinder. I'm gonna have to do the whole thing over. I don't even remember.
So are you talking about the part where you're being asked to calculate the mass? So at the beginning, that part?
It asks you it put the dice in there, and then it put the lug nut in there.
Yes.
Yeah, that part.
Because I remember it asking for volume.
And then it had the meniscus, and you're supposed to give the exact volume.
Yep.
And I was like, mm. So that's why I had issues with this one, because I wasn't even sure. Looking at that line, I thought that was 2.1, but it's not
So
2.1.
the bottom of the meniscus, you see how it's curved? The very bottom of that is
Mm-hmm.
below the 0.1. So it's in between the 0 and the 0.1. So that's why it's 2.05, because you're expected to be able to guesstimate beyond what you can read. So if I can read 2 and if I can read 2.1, then I should be able to guesstimate the next digit, which is 0.05. And that's because if I was looking at that flat on so that it's even, I can see that the bottom of that meniscus is below the 2.1.
Okay. See, I put 2.05 for the initial because I thought the given was 2.1. I thought it went up from 05 to 2.1, if that makes sense. What says initial volume of water? I put 2.1. Oh, that's the correct answer. Okay. So then volume of the water plus, oh, that's a sig fig.
See, and that's just a sig fig issue. Yeah, there. And this one is also.
And
That calculation is wrong because that first number was not correct. So that calculation would be.
okay, I got this one wrong because I put 2.1 here.
Correct.
Oh, oh my goodness. Okay.
And then that last one, the very last one, it says The mass of the irregularly shaped object is 5.75 grams. Determine its density. Report to the correct number of significant figures. So if you've gotten the right volume for the object, the 1.95, and the right, and we have that mass, we take that 5.75 divided by the 1.95.
Yep, because it would have gave me 2.948. But instead I did 5.75 divided by 1.9, and that's why I got 3.
Right, exactly. Yep. And that's, it's one of those things where, because one of the things that was reported is not correct, everything that you did based on that, according to Alex, is incorrect. But that's not the way that I typically grade. I just haven't had a chance to, I haven't gone back and looked at any of the lab stuff.
Okay, no problem. When I was at work and my Apple Watch was just like dinging, and I was like 0, 0, 0, 10%. And I was like, oh my God, what happened? Like, I just watched my grade go from an A to an F, and I was like, what the heck? And
What?
then,
And again, this is one of those things that now that I know that it's doing this, I need to go back and look at everybody else's stuff. I need to get your grades or the test done first, and then I will be able to get back in there and take a look at this.
I just, I want to, I want to do good, and
Yes. And you're, I mean,
because
really,
of
I
this.
understand.
Um,
Oh, okay, sorry.
no,
We
you're
keep
fine.
talking over each other. I understand that you may feel demotivated by what's happening. And so I need to make a comment to everybody else about what's going on. And, it's being really rigid about what it's looking for. And I have to go back and hand grade these things. But since I haven't finished your tests yet, I haven't been doing that.
Okay.
And I actually wasn't even really thinking about the fact that I needed to do that at all. But it's very true that I need to. So that's something that we're going to need to, I'll ask for a little patience, but I'll make sure that I tell everybody that, because
It's
it's not, it shouldn't be that bad. It should not be that bad.
okay. It definitely was a little defeating,
Yes. And
seeing that. So I'm
I
like,
do not want that.
I don't know if I can come back. I was like, I don't know. I was telling my mom this morning, I was like, I don't know if I can come back. And then the internet this morning, just, I don't know. I swear it's my brother in that streaming.
It may be.
I think it is. I definitely think it is. So at night I'll have to like go down there and turn off the extender or something, because I couldn't even get on this morning. But um before we go, I'm gonna work on aqueous solutions, and lecture 2 was concentrations,
Yes.
and I missed the second half of that lecture. So let's see. So got through this. Got through this. Okay, right here is where I had to get off at standardization calculation.
Okay. So when we talked about molar concentration, we talked about that.
Mhm.
How would I calculate the molarity of that KHP solution, knowing that I have that mass and that volume?
Um, I need to take the mass of the element, and
Yes.
I have KHP, which
And
is
remember, KHP is it's a really big thing. We call it KHP. It's just an acronym for what it is. It's molecular weight is given a couple slides up. I think it's 205.2, but don't quote me on that. Oh, it's right there, 204.2. You scroll down just a little bit. So we use
okay.
a standard like KHP, and KHP is KHC8H4O4. Molar mass is 204.2.
Okay. I thought I had that written down somewhere. Sure. It's lecture 6. Okay, lecture 6. Excuse me. So KHP is 204.2 grams per mole.
Yep.
And then you added 5 0 grams of this to prepare 25 milliliter. Oh, I should probably stop sharing my screen with you so I can see what you're doing on your end.
So the first thing I had to do was convert to moles. So I divided by the molecular weight. Then I have to divide by the volume, but that volume needs to be in liters.
Okay.
So that's all I've done there. That's to calculate moles per liter, which is molarity.
Okay. So 1,000 milliliters is a liter. So that'll cancel these out. Cancel this grams. KHP. I did not get that answer. I did not get that. So I have 5.123 times 1,000 milliliters, which gives me 5,000. And then 204.2 is 20. Okay, now I got it. I just gotta be careful how I put that in the calculator.
Trust me, my calculator hates me most of the time.
9794. Now, I would have gotten this wrong in Alex because of the sig figs. I wouldn't have known how many sig figs still like trip me up. We started off with 4 in
Correct.
1, 2, 3, 4. But I look at 0.974 as 5.
No, the 0 is not significant. It's a placeholder. It needs to be there so that we can see the decimal place, but that's all it is.
Okay. Okay. I count that 0 as a placeholder, and then I would have put 0.979. Then I would have gotten it wrong. Because I would have.
Nope. So that 0 does not count. It's only stuff after the decimal point that counts. So 0 is after the decimal point. If they're at the end of the number, they count. If they're at the beginning, like if this was 0.0009794, this is still 4 sig figs because those go away if I put it into scientific notation.
Okay. Okay.
And that's the rule I use is if I take my calculator and ask it, what is this in scientific notation, then whatever's left is what counts.
Okay.
And of course, this is 4 sig figs. This is 4 sig figs. This one we don't count because that's a conversion factor. So we don't care how many decimal places that or how many sig figs that is. This is considered infinite. This one also is not one we consider. So it's just the mass and the volume that we need to consider.
Okay. Okay. So then So the concentration of KHP in that flask would just be 0.9794.
Correct.
Okay. What is the unit that I would put at the
So
back of
it's big M. So either we write big M or you write moles per liter. Big M, which is molarity, stands for moles per liter. So either one is fine.
Okay. Molarity. All right. You will be on tomorrow, right?
Yes,
Okay, I don't go into work until 2 tomorrow, so I'll probably be getting on your nerves tomorrow.
that's not how that works.
Okay. Um, okay, the next one says I prepare 49.326 grams of sodium oxide? Nope, sodium hydroxide in
Yes.
a total volume of 1,000.00 milliliters to do a titration. Reacting this solution against the KHP, I find that a sample of 50 milliliters of the sodium
Yes.
hydroxide requires 49.624 milliliters of KHP to reach the endpoint. What is the theoretical molarity of NaOH? Okay. So I start off with 49.26 grams of NaOH.
Yep.
Um, um, then I do 1/1000 milliliters. And then I need to do the 1,000 milliliters to give me 1 liter.
Mm-hmm.
And that gives me what divided by 49. Oh, got the same number.
Now,
I got
what units are you currently looking at?
uh we are we want the big M here.
Yes. And is that what you have?
No, I had grams of sodium. Um
Sodium
oh,
hydroxide.
yes. But this would be 49.326 moles per liter.
But is it?
Oh,
How many moles is that? How do I find out how many moles that? What did we do in our last calculation that we haven't done yet?
we didn't get the mass. We did not get the mass of sodium hydroxide.
Correct.
That
So,
that's why I got the same answer because that's not right.
so what's the mass of sodium hydroxide?
That's in one of these papers.
Well, you can calculate it from your periodic table.
I wish cheat sheet on one of these handouts, but I have Na22.990 and then 15.999 and then 39.997. So then I have 39.997 grams per mole of NaOH. And that would just be 1 mole of NaOH. Hmm. 1,000 milliliters. 1,000 milliliters. Oh, I wrote it upside down.
Which part?
The last part. I had 1 over 1,000.
Yeah, but that's right here. So I divided by the 1,000 mils that were in the solution, but then I have to convert that to liters.
Oh, I erased everything I had and tried to put my moles in the middle.
But you
Oh.
can do that. I mean, you can set it up the same way that we did here, you know,
Mhm.
the previous one. That's perfectly fine. As long as everything cancels and I end up with moles of NaOH per liter, it doesn't matter what order I do it. That's what that's what I need.
Okay, I just confused myself going that way. I don't know. Seeing you do it this way and then me doing it the opposite way just kind of confused me a little bit.
Well, so 326 grams of NaOH,
Mm-hmm.
1 mole of NaOH,
Mm-hmm. That's what I.
39.997 grams. The grams cancel.
Mm-hmm.
I then divide by the 1,000 milliliters that it is,
Mm-hmm.
and then I convert the milliliters to liters.
Okay, and then I had 1 over 1,000, which doesn't make sense because then the milliliters would not cancel.
Yeah, we only need 1 over 1,000 once.
So I have 49 times 1,000 divided by 49, 7. Okay, so 49,362 divided by 3. 3. All right, how many sig figs, Alicia? 1, 2, 3, 4, 5, 6 sig figs.
I see
1, 2, 3, 4,
1,
5.
2, 3, 4, 5. 1, 2, yep, 5. Because this one has more than 5, but this one only has 5.
Okay. So now I have 1, 2, 3, 4. Oh wow, 1, 2, 3, 4. 1, 2, 3, 4, 1. 1.2341.
That's not what I got 1.2332.
So I did 49.362 times 1,000,
Oh,
which gave,
I thought it was 326. Did I
or
invert my numbers?
maybe I wrote it wrong.
I'm not sure because I can't see it, so I'm not looking at it.
Let me see. It's 2.6. Why did I put 6.2? I don't know why I typed
I do that all the time, which is why I asked. I'm like, wait, did I do that?
3.26
Yes.
numbers. 3,999. Now I got 1, 2, 3, 3, 2. 1, 2, 3, 3, 2. Yep, 1.332. And that unit is Big M.
Yes.
So that just answered the first part.
Yes. That
Yeah.
is my theoretical molarity. That is correct.
And it says, what is the actual molarity
Now,
of?
how do we find an actual molarity when we're talking about titration?
Mm, mm, mm. I think I have to go back to the standardization. I'm looking through my notes. Yes, I need to go back to standardization.
Okay. And what do you need from there?
KHP,
Okay. What part of it? And
the
why do
molar.
you need to go back? Yes.
I need the molar mass because I don't know. I don't know.
So if you go back a couple of slides, it's number 13. It says titration calculations. Actually, let me share this. This one right here.
Mhm.
So we have a concentration, and I know the volume of that. So if I multiply that concentration times the volume, that tells me how many moles.
Okay, see, I missed this part.
Okay. So remember that we have the reaction that we're looking at. This one, right?
Mm-hmm.
This is our KHP, and we take the K off of it, and our net ionic equation is HC8H4O4 minus plus
Mm-hmm.
COH minus, and that gives me H2O plus C8H4O4 2 minus. That's my net ionic equation. And I don't normally write the whole equation because I know that this is a one-to-one relationship. So when I write this, I write that. Oh, what the heck? Why are you not sharing anymore? Someday. So when I write this, I typically write this as NaOH plus KHP goes to water plus something, just to remind me that it's a one-to-one ratio. Okay. When I need to do is I need to know the volume and the molarity of KHP and the volume of NaOH. So it told me that I calculated the molarity of the KHP, right? I know that this is 0.9794 molar because I calculated that right there.
Mm-hmm.
I am looking for the molarity of the NaOH. That's what I'm trying to find out. I know that I used a 50 milliliter sample of NaOH, and I know that it took me 49.624 milliliters of KHP to do that titration, right? That's what it told me in the question.
49.
So in this,
Which one is that? Oh, reacting the solution against. Okay. Okay.
yeah. So I pulled that from right here. So
Okay.
49.624 milliliters KHP to reach the endpoint. So I can use that information to do this calculation. So I know that I have volumes for both of these, and it's driving me insane. I don't know why it keeps losing connection. So I have a volume for both of these and a molarity for this one. I always start with what I know the most about. right? So I will start with 49.624 milliliters of KHP that was used. I multiply that times the 0.9794 moles of KHP per liter. Of course, that's not going to work because I need to convert my milliliters to liters. So I know there are 1,000 milliliters in a liter. That'll cancel the liters. That'll cancel the milliliters. And leave me with moles of KHP.
Okay.
Once I have moles of KHP, I know from this balanced equation that 1 mole of KHP is required to react with 1 mole of NaOH. So that'll get me the moles of NaOH. And to get a molarity, I need to divide by the volume. So it's 1 over the 50 milliliters, and I can't remember how many sig figs that was. Yeah, I just had 50. And then, of course, I have to convert that from milliliters to liters. So that cancels the milliliters, and that leaves me with moles of NaOH per liter. So that's the calculation I do to find out what the actual molarity is.
Ooh, okay. I'll have to because I'm gonna let you go after this. I know you have to go. I'm gonna have to go back. We have some word problems and not the handouts, but the actual lecture worksheets. There's some word problems like this that you gave us. So I'll have to
Correct.
so I'll do
That
this.
is correct. And here's some examples.
Okay. Okay.
You'll see that that's set up the exact same way, because I always set mine up the exact same way, otherwise I get confused.
Also with the test,
Yes.
it I probably like psyched myself out. And I kept getting flagged while writing. I kept having to like put my head back in the screen and like put my pencil up like, "Hey, I'm just writing. I'm not
Yeah,
cheating."
I know it does it, but it's one that, so if I don't turn the respondus on, I have actually had students bring another person into the room.
Into the classroom?
The room that they're taking the test in,
Oh,
and
okay.
take the test for them. So I have to use that to do it. I understand that, people get out of phase with it, and I get it. And I find it really annoying, but I have to make sure that you guys aren't cheating. And
Yeah, of course.
much as I would love to say that nobody does, that's really not true. So I have to avoid it as much as possible.
I understand. I just discovered Lockdown Browser this semester, like spring 1. That
It
was
is
new to me,
not my favorite.
but it apparently has been around since 2020 when the pandemic first came, but I
Oh
hadn't
no,
never.
we had it before that. I
Oh,
I
with the
I
camera?
first used it. Yes, I first used
Oh.
it at in 2012.
What?
Yes.
Oh my goodness. I didn't even know that was a thing until this past semester, but then my friends that already graduated, they were saying like they were really cracking down on the cameras
Yeah.
when the pandemic
Oh yeah.
came. I thought that was something new that had just came out.
Oh no, unfortunately, it's not. It's
Oh, we just haven't been using it.
yeah. A lot of teachers didn't implement it until the pandemic because they didn't know how to use it. They didn't know, like what the rules were and all the rest of it. So a lot of people didn't use it, but then you get into a situation where you have to.
And now it's not going anywhere.
Oh no. And trust me, it's one of the nicer ones out there. Some of the rest of them are more.
Yeah, my friends that are in their master's programs, they have the ones like online, it like tracks your eye movement.
Yep.
And I was like,
It's to
oh,
make sure that you're looking at that computer and not another one.
uh-huh. Yeah.
because
it
that
tracks.
was something that started, and I'm one of these people. I have multiple computers, so
Mm-hmm.
it would be very easy for me to set up another computer, right next to me and use that one to do something not on the, that's outside the lockdown browser.
Mm-hmm.
I never did that, but it would have been possible for me to do it. And so that's what they caught on to, was people were using either another computer or their phone or a tablet, something to Google answers.
Okay. Yeah, I was like, I hope I don't. That was the first time I ever got flagged in lockdown browser, because I took algebra last semester, and I
Right.
never got flagged for like doing work. So I was like, maybe hers is just a little bit more sensitive than the
Well,
one from.
it's possible that the instructor had turned off the facial recognition portion of it.
Oh, okay.
But the one semester I turned it off, I was reviewing a video and I
Hmm.
saw that it wasn't the student that was in my class that was in front of the camera. So they had another person take their test.
Mm.
So they sat down, did the facial, did the ID check, the whole thing, and then stood up and let somebody else take the test.
Well, I wouldn't even have. I If this thing is looking at your face before you take it, I would assume it's looking at your face the whole time you're taking the test.
Yeah, some people really don't care, I think is what it comes down to.
It's a camera. I don't know.
They just have it fixed that they need to get this grade, and
See, I don't know, cause my coworker Ethan, he's going for his master's. He's gonna be finished in July, and he wants to teach forensic psychology. And we were just talking about what kind of professor he would be.
yeah,
I was like, "You're gonna be one of those mean professors who fails everyone." He was like, "No, as long as you try, I'm not gonna like, give you any.
yeah, yeah.
But if you like try to like, get over it, it's like, I
I
don't know."
as much as I want to be nice, there are students who really try and
Of
pull a
course.
fast one.
Yeah, yeah. That was me my senior year of high school. I was just ready to get out of there. I was just ready. I was just ready to
I have
finish. And I
no
was like,
experience with that whatsoever.
oh, okay.
That was totally sarcastic. But
Yeah, me either. No, my senior year, I was just one of those. I had like 3 classes, and I was like, why do I need to be here? I have 3 classes. I'm just ready to finish. So that was definitely me, my senior year.
yes,
Um, I'm gonna work on this and aqueous solutions, and then we have concentrations, and then we have Lewis dot structures. I'll work on that tonight as well, and then we'll have some time to tutor tomorrow. We'll have plenty of time. We'll have to rush to get off, but I can. So tonight, I need to go on Alex and do. Forgot just that fast.
the lab.
The lab.
Yeah,
Okay.
yeah. Make sure you're doing the labs before you do the post labs, because it, while it may tag you for sig figs and stuff like that, like I said, I can go back and grade that after the fact. And if that's all it is, that's not an issue. So
So I need to go in Alex tonight and do. Today is. Alex and do the virtual lab for synthesis.
yes,
Okay.
yes.
Okay. We'll get that done tonight.
All right.
Okay. Thank you so much. I
You're
will talk
welcome.
to you tomorrow.
Yes, I will talk to you tomorrow.
Have a good day.
Thanks. You too.
Bye.